Hi, everyone. Can you hear me?
Yes, we can.
Okay. Whoops. There you go. Okay, so I will share my slides now. Okay, so can you see the
slides?
Yeah,
Yep.
Thank you. Now I lost the Zoom window. Let me see if I can bring that back. Okay, so just so that you know, I cannot see anybody because I lost my gallery view of the Zoom, but I hope that you can still see the slides.
You can see the slides.
Thank you. Thank you.
Please go forward.
Okay, so today I will be talking about a procedure to adjust p-values in multiple testing in the context of addressing sparsity in high-dimensional metabolomics data. And we call this procedure DiscoPad. This is a joint work with Drs. Katerina Kekris and Debashish Ghosh in the Colorado School of Public Health. So suppose we have this metabolomics data set with n individuals, each having information on p metabolites, and we have an outcome variable of interest, and we have some clinical covariates that we adjust for. For example, we are working with the COPD gene metabolome LCMS dataset collected from the plasma samples of this TopMet cohort with about 1,050 samples and about 760 metabolites. Now the question is, which metabolites are significantly associated with the outcome? In our case, it could be some marker of this lung capacity or even the gender. To answer this question, we perform some statistical tests. Now, to achieve a desired family-wise error rate, say 5%, we need to produce metabolite-specific adjusted p-value. Why? The goal is to minimize the false positives and false negatives among the statistically significant metabolites. So what researchers have done, they have used false discovery rate or FDR, but that is mostly useful for data with non-sparse signal where we expect a lot of discoveries. On the contrary, more generally used measure or adjustment is the Bonferroni adjustment. But as we know that that's the most conservative adjustment because it assumes all the tests that we perform are mutually independent. So there is a possibility of many false negatives there. So alternatively, another way to approach is to estimate the effective number of tests instead, which we call MF in this talk. So and this could be achieved by performing an eigenanalysis of the features correlation matrix, right? For example, in our metabolomics data, it will be a P cross P correlation matrix with P metabolite abundances. And in the GWAS context, researchers have used the Pearson correlation among the, for example, the SNP values. This last method highlighted here, that's a metabolomics approach of this eigenanalysis based method. What we propose instead, that instead of using this Pearson correlation, which captures the linear association between two random variables, we propose distance correlation to do this eigenanalysis on the metabolite abundance correlation matrix and thus compute this M effective. How does DiscoPad perform? Let's see. I will show you the results of one simulation setting where we have taken 100 subsets of size, each with size 100, sample size 100 from this COPD gene metabolome data. And I will show you the comparison between 5 eigenanalysis based methods, the Bonferroni and the gold standard permutation based approach. So here we go. So the horizontal red line is indicating the original 761 metabolites. The y-axis indicates the estimated effective number of tests. The leftmost box plot corresponds to the permutation-based gold standard approach, where it estimates the effective number to be 690 or some. And these are the 5 different methods that we have compared. Each method, you can see the colors have 2 box plots. The left one corresponding to the Pearson correlation-based eigenanalysis approach. The right one corresponds to the DiscoPad-based approach. What we see is that using DiscoPad-based eigenanalysis, for each of these 5 methods, we improve the estimated effective number of tests, bringing them closer to the gold standard value. For the last 4 methods, we improve the M effective, which in turn corresponds to reducing the false positives. And in this Nyhold method, we reduce the value, bringing it closer to this again, the gold standard, which corresponds to reducing the false negatives. So what I really showed today is that depending on the p-value adjustment method used, DiscoPad can mitigate false positive and false negatives in multiple testing for sparse high-dimensional metabolomics datasets. These are the references that I have used for the talk, and it has some more as well. And I'm grateful for all the help that we have received for the work. Thank you.